Hi there. This is Sally's Book Club, bringing you the best books from around the globe every single day. Today we're exploring Blockchain, Technology Driven Finance, a book about emerging opportunities that capture everyone's attention. The fourth technological revolution, marked by big data, cloud computing, AI, and blockchain, represents humanity's most significant upcoming opportunity. Though blockchain entered public consciousness later than other technologies, it's become the cornerstone of fintech, with enormous societal impact. This book systematically examines blockchain's capabilities and its potential to revolutionize the financial sector. Originating from Princeton's Bitcoin and cryptocurrency course, lead author Arvind Narayanan and co authors bring rigorous technical perspectives. This work stands out as one of the few technical yet accessible bestsellers, thoroughly analyzing blockchain applications. The 400-page book will be presented in two parts. First, Bitcoin and Blockchain 1.0 era. Second, Ethereum and smart contracts ushering in Blockchain 2.0 era. Let's begin with Bitcoin and Blockchain 1.0. Understanding blockchain starts with Bitcoin, its foundational technology. Nearly all blockchain technologies today evolved from Bitcoin's original framework. Bitcoin emerged in 2009 as a groundbreaking cryptocurrency. While many perceived Bitcoin as sudden innovation, it actually resulted from natural evolution in digital payments. First, let's examine two key payment concepts: credit and cash systems. In credit systems, if you get soda from Xiaozhang, you create an IOU. When Xiaozhang needs instant noodles later, you settle the debt by providing them. That's how credit works. In cash systems, you directly purchase Xiaozhang's soda using physical money. Then Xiaozhang can buy noodles elsewhere, requiring only that buyers have sufficient cash for each transaction. Digital payment methods essentially fall into two categories: credit systems and cash systems. As a digital currency, Bitcoin clearly belongs to the cash system category. But to understand its unique features, we first need to examine the shortcomings of credit systems. Credit card transactions are a typical example of credit systems. For instance, when using credit cards on Amazon or JD.com, merchants gain access to your transaction details and bank account information, which could potentially be misused. Amazon has been known to adjust prices dynamically based on users' purchase histories. Sellers might inflate prices if they determine a buyer can afford to pay more, maximizing their profits. Another model is intermediary-based online transactions. Take Alipay as an example. The platform acts as mediator. You share financial details with them, they verify transactions with sellers, and handle batch settlements daily. And while this protects your credit information, it adds complexity. Both parties must maintain accounts with the intermediary. You can see both direct and mediated credit systems have inherent limitations. Now let's examine cash systems. They eliminate default risks and offer two unique advantages. First, enhanced anonymity. Cash transactions require no personal information exchange. Second, offline capability. No third-party authorization needed for transactions. Bitcoin shares similar advantages with traditional cash. While not completely anonymous, Bitcoin allows pseudonymous transactions without revealing real identities. Though not fully offline capable, Bitcoin operates through decentralized peer-to-peer networks instead of central authorities. Every participant acts as a network node. No central server exists, with information shared through user clusters. This network architecture demonstrates remarkable self-healing capabilities. So how exactly does Bitcoin's blockchain technology enable these digital cash functionalities? Let's dive into the Blockchain 1.0 era and explore Bitcoin's principles and characteristics. First, let's understand what cryptocurrency really means. All currencies require mechanisms to control total supply and prevent fraudulent activities. Take the US dollar. The Federal Reserve controls issuance, while physical bills incorporate anti-counterfeiting features. But technically, counterfeiting physical currency remains possible. During wartime, nations might counterfeit enemy currencies to destabilize economies through aerial distribution. Just physical currency has inherent security and transactional limitations. Since the 1970s, global efforts have focused on developing more secure digital currencies. Digital currencies require safeguards against counterfeiting and overissuance by malicious actors. They must also prevent double spending, dishonest users spending the same digital funds twice. Unlike physical cash that can't be duplicated, digital data could theoretically be copied endlessly. Cryptographic solutions emerge to address these digital currency challenges. Digital currencies differ fundamentally by using cryptography instead of central institutions for security. Bitcoin employs hash functions, digital signatures, consensus mechanisms, and blockchain architecture to ensure security. We'll skip detailed cryptographic explanations and focus on two core concepts today. Understanding distributed ledgers and consensus mechanisms will reveal Bitcoin's essence. When you encounter other blockchain projects beyond Bitcoin, you'll be able to grasp their fundamental principles. Let's first understand distributed ledgers, contrasting with the centralized ledgers we commonly use. For example, if you deposit 10,000 yen in your ICBC account, why does a digital entry make you feel wealthy? Essentially because ICBC records your balance, which is ultimately tracked in the central bank's ledger. The central bank currency issuer operates under national sovereignty's guarantee. All transactions through commercial banks like ICBC and CCB ultimately register in the central bank's unified ledger. This centralized ledger exists as singular authority. Only the central bank can modify entries, ensuring monetary system stability and authority. Your 10,000 yen security ultimately rests on national sovereignty's guarantee. That's centralized accounting. Now, let's examine Bitcoin's distributed ledger concept. Bitcoin's system has no central record keeper. Every participant maintains the ledger. If Longer owns 10,000 yuan and John Sun transfers 3,000 yuan to Li Si, this transaction gets recorded in everyone's ledger through distributed consensus. To commit fraud, one would need to alter all existing ledgers simultaneously. This makes tampering practically impossible. Thus, distributed ledgers create secure cash systems without central banking. Now comes the second challenge: continuous ledger updating. Who gets to update this constantly evolving ledger? This introduces blockchain's second key concept: consensus mechanisms. Simply put, rules determining who can add entries to the shared ledger. These entries contain vital information: Bitcoin ownership and transaction records. Ensuring recording fairness and legitimacy becomes absolutely crucial. Bitcoin's consensus mechanism is called proof of work. Simply put, anyone wanting to validate transactions must connect computing devices to the network and solve complex mathematical puzzles. The solution is then broadcast to all network participants for verification. The first to solve the puzzle and gain majority validation earns the right to record transactions. This computational process resembles gemstone mining, hence called mining in blockchain context. What does the successful miner do next? They package all pending transactions from the past 10 minutes into a block. This block gets added chronologically to the existing chain, becoming the newest verified transaction record. All participants update their ledgers with this new block, completing the validation cycle. Successful miners receive newly minted bitcoins, the currency's issuance mechanism. Every 10 minutes, a new block joins the time-ordered chain, hence blockchain terminology. What advantages does this system offer? First, complete transparency. The entire blockchain is publicly accessible. Every transaction becomes immutable and traceable, eliminating fraud possibilities. Each Bitcoin transaction has unique cryptographic signatures validated through consensus. Second, pseudonymous transactions using alphanumeric addresses. instead of real identities. The blockchain only shows address A sending X Bitcoin to address B, protecting user privacy. Bitcoin's blockchain system implements an incentive mechanism. Mining both validates transactions and issues new coins. Initially, miners received 50 Bitcoin per block, halved every 210,000 blocks, approximately 4 years. Around year 2014-01, Bitcoin's smallest unit, 1 Satoshi, equals 0.0000001 Bitcoins, becomes indivisible. Total supply caps at 21 million Bitcoin, enforced by network consensus through programmed scarcity. Eliminating centralized institutions reduces operational costs, potentially revolutionizing financial efficiency. We've covered Bitcoin's foundational principles. Now let's examine real-world applications. Bitcoin's potential extends beyond currency. It could become programmable digital property. Each Bitcoin transaction carries immutable timestamps recording its entire ownership history. This permanent audit trail enables revolutionary applications beyond financial transactions. How exactly do these timestamps create value? Beyond transaction tracing, blockchain timestamps could verify intellectual property ownership. Artworks or music registered on blockchain would have indisputable creation and transfer records. Counterfeiting becomes nearly impossible. Buyers can verify ownership history instantly. Now let's address Bitcoin's environmental considerations. Like gold mining's ecological impact, Bitcoin mining consumes significant energy resources. Wait, digital currency requiring no physical extraction? How does that cause pollution? Remember Bitcoin's creation mechanism? Proof of work requires massive computational power. Specialized mining rigs, essentially high-powered computers, solve cryptographic puzzles. From manufacturing to operation and cooling, every stage consumes substantial electricity. How much electricity does the entire Bitcoin network actually consume? The author estimates it's equivalent to hundreds of megawatts, nearly matching Denmark's national energy consumption. Some propose repurposing mining heat as data furnaces for residential heating. Perhaps future homes will use blockchain-powered heaters instead of traditional systems. We've examined Bitcoin as Blockchain 1.0, establishing digital cash systems through distributed ledgers. But asset transfers often involve complex narratives beyond simple transactions. Insurance payouts after car accidents or delivery fees upon package arrival, these require contractual frameworks. This need birthed Ethereum, the second-generation blockchain platform. While technically similar to Bitcoin, Ethereum introduced a revolutionary concept: smart contracts. Let's explore Ethereum and smart contracts, the foundation of Blockchain 2.0 era. This evolution enabled diverse applications, from insurance to stock trading, fueling recent blockchain growth. Ethereum combines its native currency, ETH, with programmable contracts deployed on its network. Traditional contracts face two critical issues. One, textual ambiguity, different interpretations of contractual terms. Enforcement costs, legal proceedings for contract breaches. Smart contracts solve these through code-based execution. How? Let's demonstrate. Imagine developing a mobile app that a company wants to acquire by year-end. You could program an Ethereum contract specifying transaction date, payment amount, and IP transfer conditions. Then upload it to the Ethereum network. The company can review the contract and deposit the agreed amount of ETH, which automatically executes upon the specified date. No centralized authority mediates. Instead, a transparent smart contract, visible to all network participants, governs the process. Code eliminates ambiguity. Year-end means December 31st, not lunar calendar dates. Removing contractual breach risks. Smart contracts both define terms and enforce execution. That's their revolutionary power. This dual capability makes Ethereum the backbone of Blockchain 2.0's explosive growth. Blockchain's transparency resolves trust and security issues inherent in traditional transactions. Moreover, blockchain streamlines financial operations efficiency. Multi-party financial processes often suffer from slow processing due to complex workflows. Consider international transfers. They incur fees and delays due to currency conversion and banking protocols. Manual verifications between disparate banking systems create these inefficiencies. It's an outdated, resource-intensive process. Essentially, cross-border transactions are multi-party contract validations, perfect for blockchain solutions. Implementing Forex agreements through smart contracts automates settlements and reconciliations. Institutions adopting this system benefit from instant settlements, error reduction, and standardized protocols. Now you understand blockchain's core value proposition. Blockchain creates open, transparent, and trustworthy accounting systems, as demonstrated by Blockchain 1.0's. Bitcoin's distributed ledger and consensus mechanisms create a secure cash system resistant to counterfeiting, tampering, overissuance, and double spending. Blockchain 2.0's smart contracts on Ethereum solve trust issues while enhancing financial efficiency through automated execution. The authors envision blockchain evolving to transform commercial and social systems, from real estate to governance. Blockchain could revolutionize platforms for housing rentals and voting systems through transparent record keeping. Understanding blockchain's core principles positions you to capitalize on its impending transformative wave. This concludes our analysis of blockchain, technology-driven finance. Find key takeaways below. Until tomorrow,